All right, good morning, good morning. We are going to be talking about music today, so ending our sound wave series. All right, so we're going to talk about how music really relates to physics, all right? And we should know it by now because music is a sound, and we have been talking about sound waves for the past couple of weeks. All right, so the other day, whenever we looked at the tuning fork, we saw that once it was struck, the ends of it began to vibrate back and forth. And it's those vibrations that give off the sounds that we heard. All right, so that brings us to this one. It says a sound wave is just created by the result of a vibrating object. All right, so the tuning fork was just an example of that. So whenever we're talking about music, of course, we're going to be talking about singing. All right, so if you were to make a noise and put your hand on your throat, you would hear your vocal cords vibrating. All right, so your vocal cords are producing those sound waves. All right, so think about a guitar, that vibrating string on a guitar. On an acoustic guitar, then you have your electric guitars. They do not have the same kind of thing, and we'll talk about that later. All right, but the soundboard of a guitar, all right, you've got a reed that vibrates in a clarinet and all of those different things. There's just a ton of different vibrating objects that are involved in music, and that's just going to be your source of sound. Yesterday, we talked about resonance, and we talked about how every single thing vibrates at a natural frequency. All right, so every single object, all objects have a natural frequency that they vibrate whenever they're struck. All right, so whenever we pluck a specific guitar string, that guitar string has a natural frequency. Even if you talk about dropping a pencil, you strike it, that would be striking it, it's going to vibrate at its natural frequency. All right, so it's that frequency that we're looking at whenever we're talking about sound. All right, so now we're going to talk about the quality of sound, and that comes with something called timbre. All right, so timbre is just the quality of sound produced, and it has to do with the natural frequencies of the sound waves. All right, so timbre itself is what makes a musical note sound different from another one, and it also makes one musical instrument sound different from another, even if they're playing the same musical note. All right, so if you have something that say is described as a pure tone, that is going to be caused by a single frequency. If you have a rich or a round tone, that is something called or produced by a set of frequencies. All right, so this is just giving timbre is just giving a specific musical instrument its own sound. All right, so it's going to sound different than, sorry, I've had students walk in that we're not supposed to, and they're distracting me, so give me 5 seconds. All right, so timbre is just what makes all of these different sounds different from each other. All right, so say that you're playing middle C on a piano, and then you play the exact same note on a trumpet. Even though they're playing the exact same note, you would be able to tell the trumpet from the piano. All right, so it's timbre that gives it that difference. All right, now we have the fundamental frequency. So we mentioned this at the very end of waves last week. All right, so fundamental frequency is just the lowest frequency that is produced by any instrument. All right, so fundamental frequency, we saw this with standing waves. These frequencies are going to be produced by standing waves. All right, so you see that this fundamental frequency over here has one antinode with two nodes. All right, so that is called the fundamental frequency. Fundamental frequency is also called first harmonic. It's called first harmonic because it's only got one single antinode. All right, so we're going to be talking about more than just that first harmonic. And all of these are just going up in whole number multiples of the fundamental frequency. So we have first harmonic, second harmonic, third harmonic, fourth, fifth, sixth, 100th harmonic. All right, so all that really has to do with is how many antinodes that it's going to make. So it includes the fundamental frequency and all of the whole number multiples following it. All right, so if you look at it, we've got our wavelength. So that's the wavelength of the first harmonic is just equal to 2 times the length of the whole string. All right, because we see that in our fundamental frequency or our first harmonic, we're only making half of a cycle or half of a wave. So if we wanted to make a complete wavelength, we would have to double the length of the string. All right, so this is F1. So that's our fundamental frequency. So that's what you see right here. Now, if we were trying to solve for the wavelength, we could rearrange this equation. So our wavelength would be, or I'm sorry, if we were trying to solve for length, so get length by itself. All right, so if we have the length, we can just divide by 2. And so our length is just 1/2 of the wavelength, or just our wavelength over 2. And we're going to see this a little bit later. So if you don't write it down now, it will be there later. All right, with this one, we have our second harmonic because we have two antinodes on this string. All right, so if you notice these two antinodes, they do make one complete wave or one complete cycle. So our wavelength is just equal to the length of the string. All right, so we could rearrange that and just say that the length is equal to our wavelength. All right, so this is our second frequency, our second harmonic. That's what you see as F2. So we would just take 2 times our fundamental frequency if we were to find that. Okay, now we have our third harmonic, and you guessed it, it's called third harmonic because it's got 3 antinodes. So right here, we know that we have one single wavelength is right here. So we technically have 1.5 waves on this length. All right, so if we were to solve for the length, we would just have 1.5 times the wavelength. All right, and once again, we are given the third harmonic. So this is our third frequency. So we would just have 3 times the fundamental frequency. And we're going to get an equation for this, a simpler equation for this in just a second. And once again, looking at fourth harmonic because it's got 4 antinodes. You see that one wavelength is half of the length. So that's what we're seeing here. So the wavelength of fourth harmonic is half the length of our entire wave. All right, so the length, if we were to rearrange it and solve for length, it's going to be 2 times the wavelength. All right, so this, if you were to look at it online, it would give you the animation. These are all just standing waves, right? This is an animation that's just showing standing waves. So you have this going up and down, up and down. This would be going up and down, up and down, up and down, up and down. All right, so what it's showing you is just the nodes versus the antinodes. So you are going to have to remember that nodes are the points at which there is complete destructive interference, and then the antinodes are where we have constructive interference. So our fundamental frequency has 2 nodes and 1 antinode. All right, our second harmonic has 3 nodes with 2 antinodes, and then third harmonic has 1, 2, 3, 4 nodes with 3 antinodes. So you are going to have to be able to label those later on. All All right, so let's not look at this just yet. So we have on a piano, the note middle C has a fundamental frequency of 262 hertz. We want to know what the second harmonic of this note is. All right, so what we're doing is we're kind of making a generalized equation similar to what we saw up here. All right, so write this down, put it at the top of your paper. You are going to have this on your test, but you do need it for your worksheet today and our next one. All right, so we know that we have F sub H sub X is equal to F sub F times X. All right, now let's break that down. So we know that F sub F, this is going to be our fundamental frequency. This is the frequency of some harmonic. All right, so we're looking at some harmonic. And then the X is just going to be whatever number harmonic we are at. All right, so let's put that into play. All right, so we are looking for F sub H sub 2 because we are looking for the second harmonic of this note. So we're looking for FH2. That gives us the fundamental frequency times 2. All right, so we know our fundamental frequency was 262. We just multiplied that by 2, which does give us 524 hertz. So if our fundamental frequency of middle C on a piano is 262 hertz, that means that second harmonic, the frequency, is going to be 524. All right, so easy peasy lemon squeezy. All right, for this one, the fundamental frequency of a vibrating string is 80 hertz. What harmonic would the same string be in if it has a frequency of 560 hertz? All right, so for this one, we are given the whatever harmonic frequency is. We are asked to find what harmonic it's actually in at this frequency. All right, so we're going to take that same equation. So we have FHX is equal to F sub F times X. Now, hopefully you realize that we are trying to solve for X right there. So how are we going to get rid of our fundamental frequency? Hopefully you said we're going to divide by it. All right, so we know our harmonic number is equal to our harmonic frequency over our fundamental frequency. So we know that that is 560 hertz over 80 hertz. So if we divide those two, we do get 7. So that tells us that we are in the 7th harmonic. Okay, moving on, still talking about those standing waves. All right, so we've seen these before. All of these are standing waves, and we know that standing waves have both nodes and antinodes. All right, so first harmonic, let's label them. So we have a node here, and then we have a node here, and right here is our antinode. So we have 2 nodes, 1 antinode. For this one, we have 3 nodes and 2 antinodes. For third harmonic, we have 3 antinodes and 4 nodes. So please, please, please make sure that you know the difference between all of those. All right, so each and every node is separated by a distance that's equal to half of the wavelength, So if we're trying to figure out the length of the string that we're on, all right, for the first harmonic, it's going to be half of the wavelength. All right, so we know that the length is going to be half of a wave because that's all we've got right here is just half of a wave. Well, we know for second harmonic, the length is going to be 1 whole wavelength. So our length is going to be equal to the wavelength. And that should have had a length equals right up there. All right, for third harmonic, so we know that it's going to be 1.5 waves. So the length is equal to 1.5 times the wavelength. What do you think fourth harmonic would be? Hopefully you said 2 times the wavelength. What do you think fifth harmonic would be? Hopefully you said 2.5 times the wavelength. Sixth harmonic. Woo, let's keep going. We can go on forever with this. All right, the length is equal to 3 times the wavelength. All right, so we're just going up by increments of 0.5 whenever we're doing this. All right, so let's put that into play here. All right, we know that the string below is 1.3 meters long. So we know that the length is 1.3 meters long, and it's vibrating as the fourth harmonic. Well, we didn't even have to be told that because we have 4 antinodes. That already tells us that we are in fourth harmonic. The string vibrates up and down with 48 cycles in 20 seconds. That should sound super familiar. We want to determine the frequency, the period, the wavelength, and the speed for this wave. All right, so we know we're in fourth harmonic. That's easy. We weren't really asked about that, but we were told that it vibrates at 48 cycles in 20 seconds. So that is number of cycles per unit of time, which is a frequency. So it's giving us a frequency. We just have to put it into hertz. All right, so we divide 48 cycles by 20 seconds. So our frequency is going to be 2.4 hertz. 2.4 hertz. All right, so that's the first thing that we were asked to find. The second thing that we were asked to find was period. Well, hopefully you remember that period and frequency are inversely related. So we just take the inverse of the frequency. So that's 1 divided by 2.4, which does give us a period of 0.42 seconds. All right, so what that means is that one cycle will go by every 0.42 seconds. The third thing that we were asked to find was the wavelength. All right, so we know that the length was 1.3 meters, but one wavelength is just half of it. All right, so if we are looking for the wavelength, we take half of the entire length. All right, so we know that's 1/2 of 1.3, which does give us 0.65 meters. So it's half of the length. And then what's the last one? Speed. All right, so we know that the speed of a wave is equal to frequency times wavelength. Hey, we have both of those. So our frequency is 2.4 hertz. Our wavelength is 0.65 meters. We multiply those and we do get 1.56 meters per second. So this string is vibrating at 1.56 meters per second. Woo! All right, so let's put that into action here. This is what your homework is going to be today. All right, so on this slide, you are given something that is in fourth harmonic. All right, you should be able to recognize that because we've got 4 antinodes. All right, what you are given for this is the frequency of 80 hertz and then the length of the string, which is 6 meters. All right, so that's all we've been given, and we should be able to find the rest of these just by being given those 2. All right, so the very first thing that I want to find is the period. All right, so if we were given the frequency up here, we know that the period is equal to the inverse of the frequency. So we just take 1 over 80. So our period is going to be 0.0125 seconds. All right, so that means that one cycle goes by every 0.0125 seconds. All right, so we're asked what harmonic we're in. All right, we've already answered that. We can tell by the antinodes we are in the fourth harmonic. All right, so the next one, could humans hear this frequency? Well, you're going to have to remember that humans, our audible sound range is anywhere from 20 hertz to 20,000 hertz. All right, so what is that answer? Could we hear an 80 hertz frequency? The answer is yes, absolutely. All right, the next thing that it asks you to do is mark the nodes and antinodes. So we've got 1 node, 2 nodes, 3 nodes, 4 nodes, and 5 nodes. Right here, we've got our first antinode, our second antinode, our third antinode, and our fourth antinode. Okay, now look at this. How many wavelengths do we have? All right, so if we were to turn this over, make it horizontal, you should see that we've got one right there and another one right there. So we have 2 wavelengths on the fourth harmonic. Okay, so what would that mean? What is a wavelength for this? All right, so we should know that a wavelength is equal to half the length of the entire wave. All right, so we would divide 6 by 2, or just take half of 6, which is going to give us 3 meters. And then this one, I want you to put a star by this one. All right, I want to know the 5th harmonic frequency. Okay, so this is kind of tricky because we don't necessarily know what the fundamental frequency was. So we've got to find what the fundamental frequency was in order for us to find the next harmonic frequency. All right, so what that means is that we have to use that same equation all over again. So FHX is equal to the fundamental frequency times the harmonic. So we know the 4th harmonic is going to be vibrating at a frequency of 80 hertz. So we're going to get rid of that harmonic, get the fundamental frequency by itself. So we have 80 hertz divided by 4, because that's 80 hertz is what we were given up here. And we know that it's the 4th fundamental frequency, or the 4th harmonic, not 4th fundamental frequency. All right, so 80 divided by 4 does give us a fundamental frequency of 20 hertz. Now, that's not what we were asked. We were asked for the 5th harmonic frequency. So now we have to use this and plug it back into this equation all over again. All right, so let's use it again. So we have FHX, which is what we're solving for here, is equal to our fundamental frequency times our harmonic. So we have 20. And we are using, or we're finding the 5th harmonic, so 20 times 5 does give us 100 hertz. So our 5th harmonic frequency is 100 hertz. And last but not least, we are asked to find the speed of the wave on this string. So remember, our velocity or speed is equal to our frequency times our wavelength. Our frequency we were given was 80. And our wavelength is 3. So 80 times 3 does give us a speed of 240 meters per second. Woo-hoo! All right, so I hope you know how to do that, because that is what your homework is on right now. All right, or after you get done with these notes. So hopefully it's getting a little bit easier for you as we go through it. All right, now we're going to be talking about music intervals. Music intervals. All right, so there are 2 different types of music intervals, and that's something called dissonance and something called consonance. All right, so what dissonance is whenever you have 2 or more different pitches that are being played at the same time that are very, very, very unpleasant. All right, so we call this a lack of harmony. All right, it's a lack of harmony. It just sounds bad whenever these frequencies are played or sung together at the same time. Now, think about this. Think about a baby crying, a person screaming, and then an alarm going off all at the same time. This is like a day in the life of Miss Bailey right now. All right, so all 3 of those happening all at the same time. That is not pleasurable. All right, so that is very, very, very unpleasant to the ear, kind of stressful. All right, gives you anxiety. All right, so that would be an example of dissonance. Consonance, on the other hand, is wonderful. That's whenever 2 different pitches or 2 different frequencies are played at the same time that sound pleasant. All right, so these things are in harmony. Oh no. and they are in harmony. They sound beautiful together. They sound pleasant together because of the relationship between their frequencies. All right, so it's because of the relationship between their frequencies, and this is the relationship. All right, it's because they are based on whole number ratios. All right, so these are those intervals and ratios that make things in consonants. All right, so this is what makes them sound in harmony. All right, so you have things that are played in unison, also called an octave. All right, you have major and minor third, major or minor third. And then you have the perfect fourth, and then you have the perfect fifth. All right, so all of these are different intervals that can be played that make something or make these sounds in harmony. They make them consonant. All right, so the frequency ratios for an octave are 2 to 1. So you have 1 being your double being your 512, and you would just half that to give you your 256. All right, so they're just ratios of frequencies, all right, that you see right here. All right, so an octave would be a 2 to 1 ratio. A third would be a 5 to 4 ratio. The perfect fourth would be a 4 to 3 ratio, and then the perfect fifth would be a 3 to 2 ratio. All right, so let's look. This is our last example. Y'all, get ready. This is the last set of notes for this class. Woo-hoo! All right, so let's do this. All right, so we have two musical notes that have a frequency of 2 to 1 and are said to be separated by an octave. All right, so that's what we saw up there. A musical note that is separated by an octave from middle C, 256, has a frequency of what? All right, so we are going to say that middle C is the higher octave. All right, so that's going to be the 2 in our 2 to 1 ratio. So what we're trying to figure out is that 1. Well, how would we do that? We would just half it. So we just take 256, divide it by 2, and we do get 128 hertz. 128 hertz. All right, so an octave down from that middle C would be at 128 hertz. All right, guys, that is it. Get ready for this simple harmonic review that you're about to do, and we'll do some more practice tomorrow. Y'all have a fantastic day. I'll see you later. Let me know.